Javier, thank you for inviting me to be part of this event. And you already acknowledged my contributors from NOAA PSL, NRL Monterey, and NRL Stennis. A lot of this work was started when I was at NRL and was finished up when I moved to NOAA. And if you want to have more details about this talk, there is a accompanying paper in Monthly Weather Review. Okay, so for a while, this was a slide that I was presenting when I was talking about coupled data assimilation, and the point was that we're all excited to develop it, right? So we have well-established data assimilation systems for ocean and for atmosphere, but what we really want to capture is cross-fluid correlation that exists between the fluids, or we want to be able to assimilate satellite observations that are sensitive to both ocean and atmosphere. But today, I want to ask a different question. So I want to ask when an ocean atmosphere are highly coupled. So when we're trying to build our experiments with our new tools, when do we expect to see a strong signal and see a strong improvement to our forecast and assimilation systems? So to answer this question, I used a coupled model that the US Navy have developed recently, and it had sea ice component, atmospheric component, and ocean component. This specific version did not have waves, and they were coupled using ESMF couplet. So the thing that were unique about this model was the high resolution of all the components. So the atmosphere was at 1/3 degree, the ocean was at 1/12 degree, and so was the ice. We have 16 ensemble perturbations initialized from our observation data simulation system. We had no coupling in the data simulation cycle, so it was a weakly coupled system, but we did have a state-of-the-art data simulation systems in each fluid, hybrid for devar atmosphere and 3devar for ocean ice. What I worked with was a 52 weekly forecast from this weakly coupled ensemble reanalysis, so it was a year-long time series of weekly forecasts. And the way I worked with it was, first, I would average the ensemble perturbation over the 24 hours, then compute ensemble correlation matrix, ensemble covariances over these 24 hours, and then I'll average 52 weekly forecasts to compute an annual average of what essentially is a short-term forecast error covariance. So to kind of mimic what we do in data simulation and to beat down the noise. I will talk about three aspects of this work. First, about the coupling of SST to the lower atmosphere. Then I'll talk about coupling of atmospheric wind with mixed layer depths in the ocean. And I'll conclude by talking about impact of model resolution. So let's talk about coupling between SST and atmosphere. So one way to go about it is to look at correlation between sea surface temperature and wind speed. So it's a very convenient correlation to look at because it reveals the direction of the flux. Is going from ocean to atmosphere or from atmosphere to ocean. So here in this figure, it's essentially a frequency. It's a frequency of the sign of correlation either be positive, the red colors, or negative, the blue colors. If the correlation between SST and wind speed is positive, it means that the ocean is driving atmosphere, and if it's negative, it means atmosphere is driving the ocean. Now, talk into mechanism behind it in the next slides. But looking at this figure, we essentially found three regimes that we would like to discuss. It's not an exclusive list, but this is the top three contenders. So the first one is the one that is well described in the literature, and it's coupling between regions that are rich in oceanic fronts. So for example, here I show the average SST gradients, and not surprising, you see Gulf Stream, so all the western boundary currents, Gulf Stream, Horatio, Antarctic circumpolar current, tropical East Pacific coltan, and a little bit of east boundary currents. And over these regions, we see that there is a often and strong positive correlation between SST and wind speed. The second regime is a complete opposite. and it's prevalent over tropical warm pool, Indian Ocean, and somewhat over the subtropical convergence zones. And if you look at corresponding physical parameters, this is tend to be regions with the shallow mixed layer depths and a lot of convection. And I will show later that those are the regions where atmospheric convection drives ocean variability. And the last set of regions is mid-latitudes. So I'm highlighting here South Pacific, but you can find the same in North Pacific, North Atlantic, South Atlantic. Essentially what happens in mid-latitudes is the sign of correlation flips between positive in local winter and negative in local summer. So the depth of the mixed layer determines the direction of the flux. So let's walk through these three cases. And the first case is western boundary currents, or boundary currents in general, the areas where we have a lot of eddies. And if we examine correlations here, so here's the annual average of SST and wind speed correlations. So you could see those correlations are positive, means that warm SST results in higher winds, higher temperature, and higher precipitation. So the work on these principles goes back to some of the work by Wallace in 1989 and some of the foundational papers by Shelton in 2001. And I'm adopting here a picture from Franger, who explained this process very concisely. So the way it works, if you have wind blowing an ocean eddy, in this case it will be a warm core eddy, a few things happen. As the wind goes over the eddy, the boundary layer warms up and expands. As the boundary layer expands, you develop more clouds and more precipitation. So that would be similar to how a bank of clouds is going over the mountain. What else happens is that the wind speeds up. And the reason it speeds up because it's going to drain more momentum from free troposphere, which usually has higher winds. And as a result of speed up in wind, you increase heat fluxes, sensible heat fluxes. And finally, as the wind enters the warm core and exits the warm core, you form areas of divergence and convergence that have associated gravity waves during the front regions. So that's a very well understood and documented mechanism of interaction of eddies with atmosphere, and it's been documented that over regions like Gulf Stream, this impact and propagate all the way to tropopause, and can have a downwind impact through the rain train through most of the northern hemisphere mid-latitudes. So second case is tropical warm pool. Why don't I switch to the pointer? Probably be useful. So tropical warm pool and subtropical convergence zones. So what you see in these regions is that warmer SSTs correspond to lower winds, higher shortwave flux, so less clouds, and less precipitation. So schematically, you could reproduce it as following. So during periods of reduced convection, or more precisely, in ensemble members with less convection, we will also have lower winds, less precipitation, and fewer clouds, which means we'll have increase in shortwave flux to the ocean. So if you have lower winds and more solar flux, what happens is that your mixed layer depth gets shallower and it gets warmer. So that's how you connect convection, the strength of convection and clouds, to the SST temperature. The opposite happens in ensemble members that have more convection. You have higher winds, more precipitation, more clouds, and less shortwave flux. Higher winds mix up the mixed layer depths, and through less solar flux and through mixing, the temperature of SST drops. It's important to note that this case can only happen when the mixed layer depth is shallow to start with, so less than about 20 meters. So, and the third case is when the depth of the mixed layer determines the direction of the flux. So here we have two regions, North Pacific and Indian Ocean, and on the top plot I'm showing the average wind speed and the mixed layer depth. And you can see that the mixed layer depth in mid-latitudes track the wind speed. Actually, even in the tropical Indian Ocean, the two track each other very well. And you could kind of separate it in two periods, when the mixed layer depth is shallower than 20 meters and when it's deeper than 20 meters. So in Indian Ocean, it's pretty shallow most of the time. But once you cross this 20 meters threshold, in Indian Ocean, the correlation between wind speed and SST changes sign. And the same thing happens in North Pacific. So my explanation is as following. So when the mixed layer depth is shallow, such as summer in mid-latitudes, your wind stress can actually affect the mixed layer depth and SST through mixing of waters from below mixed layer. As a mixed layer goes below 20 meters, wind mixing alone is not sufficient to really affect the temperature of the water or the mixed layer depth itself effectively. So you also have to add convective mechanisms for this to happen, or at least it doesn't happen in 24 hours. You need more sustained wind events, more sustained perturbations. The opposite, when the mixed layer depth is deep, I think what happens is not so much a physical mechanism, but an artifact of data assimilation. So recall that our accuracy of specifying SST is somewhere between 0.5 Kelvin, 0.7 Kelvin. So as different ensembles members evolve in North Pacific in the winter, they will have up to 0.5 degree Kelvin difference between each other. And as a storm track blows over the Pacific, this sustained 0.5 Kelvin difference will actually affect atmosphere. So it's not a physical mechanism per se of actual physical perturbations in the ocean driving atmosphere. It's more of a coupling of uncertainties. So to wrap up the talk, I'll talk about coupling between wind and mixed layer depths real quick. So the way to introduce it is to look at the instantaneous perturbation, and it's not surprising. So I'll look at the wind speed and mixed layer depth correlations. And you could see that they're high in areas outlined by this red curve. And this red curve is places where mixed layer depth is shallower than 20 meters. So you could see here's a picture of mixed layer depth shallower than 20 meters. And this is also areas where the wind speed is low. So it's either all of the Indian Ocean, which is in the off-monsoon period, or it's these frontal regions in the North Pacific, or the doldrums of the Pacific Ocean convergence zone. So it's the same mechanism. You have shallow mixed layer depths, and the small perturbation in wind can really affect the mixed layer depths if the mixed layer depth is shallow. What it also means that you have to resolve the first 20 meters of the ocean to really capture these effects. And a lot of early generation of models had vertical resolution of the order of 10 meters, which is not sufficient to resolve these processes. So let's talk more about model resolution in conclusion. So I compared the experiments that I just talked about here, where ocean was eddy resolving, or 1/12 degree, to the eddy permitting ocean, 1/4 degree. A few things happen. So as you expect, the eddy activity decreases. So this ISDA-Online of SST variance is much smaller in a quarter-degree ocean. You still see all the boundary currents, and you still see that there is a reverse correlation between shortwave radiation and SST in the boundary currents. But what you start seeing that the ocean starts responding more linearly to perturbations in shortwave. You give it more shortwave, and it warms up. If you have an eddy resolving ocean, this relationship is more convoluted. It doesn't respond as linearly. If you go to 1 degree, the ocean becomes a complete slave to the atmosphere outside of tropical Pacific equatorial time. And you start to really overestimate the correlations between ocean temperatures and atmospheric temperatures. So the lesson from this slide is, because of computational constraints, we'll probably be doing a lot of our development work in a 1 degree models. But we really should be careful about imposing lessons from 1 degree models to what real world looks like. Finally, to conclude, I think we have a strong hypothesis for potential impact of coupled data assimilation. We probably can improve winter storm predictability through interaction of western boundary currents with tropospheric interactions. We also have possible strong indication that as we go to convection resolving models, especially over tropical oceans, and especially as we try to resolve the MGO, coupled data assimilation will start playing a bigger role. It also is possible that atmospheric observation can provide additional observational constraint for western boundary currents that are currently underobserved. And finally, we finally have tools to start working on coupled data assimilation. We have a whole slew of coupled models: ECMWF IFS, CSM, NOAA UFS, US Navy has a coupled model. And we have tools in the data assimilation side. We have JEDI, DART, TDEF. So it's time to work to start testing these hypotheses above. And if you're a junior scientist and you want to work on it, please come join us at NOAA PSL series. We're having an opening right now, and we'll start developing short list next week. Thank you very much.
Thanks, Sergey. I like how you entice people to go there with a picture of the beautiful Rockies. So we have questions in the Etherpad. The first one comes from Philip Brown in ECMWF. So he's asking you, as I understand it, you are using a year-long sample to produce your covariances. Do you account for the seasonal cyclone in this? And his second question is, do you think that an ensemble of coupled models will have appropriate spread for cross-components errors of the day?
Great questions, Phil. So the paper does describe the seasonal cycle, and you definitely see seasonal cycle in mid-latitudes. You see seasonal cycle in the tropics as it pertains to monsoon going up and down. You see some size in the seasonal cycle in the western boundary currents. As for the spread, we had decent spread in the ocean. Our atmosphere was very underspread as we started increasing, and that was a known fault with our system development. And this, we should revisit some of these metrics once the spread is properly calibrated.
Thank you. And the next question comes from Laura Slivinsky. She's also from NOAA. She's asking, do you think it could be considering how we could take advantage of the spatial structure of these correlations when developing the strongly coupled DA methods?
I think it's an open research question. I'm saying that the spatial structure was one thing I didn't look here, and that's an obvious next thing to look at.
Lots of work to do in the future then. Those are the two questions that we have. If there are no further questions, then we can move to the next presentation.